class. This is our sixth in a series of lectures. I'm getting a little better at it every time, maybe. In fact, I forgot to draw my lines the last time, so let me draw those so that I can scan these in and send these out to you. Okay, so in this lecture, yes, oh, wait a second. Sorry about that. I forgot to put my headset on. I hope that you were actually able to hear me. Sixth lecture, and this lecture is going to deal with resonance and what resonance is and how we can use it to our advantage. So let's think of a circuit, a theoretical circuit. And in this circuit, we have a, well, let's say it's 10 volts peak, right, coming in. And we have a resistor. And let's say that this resistor theoretically is just 1 ohm, right? And then we've got an inductor in series with that resistor, just like we did the last time. And I'm going to say that the inductor is still 0.1 henries or 100 millihenries, however you want to think of it. But, you know, when we're doing the calculations, we've really got to do it in henries because, you know, we've got to use the composition of primary units that defines it as a primary unit. So we also have a capacitor, and this capacitor is going to have a 1 microfarad capacitance. So just like we did in the last circuit analysis that we did in lecture 5. So when you look at these, you can see that this one, the reactance here, if you think of these impedances, right, Z sub R equals 1 ohm plus J0, right, ohms. And then we could also write Z sub R as 1 ohm at an angle of 0 degrees in phasor form. When we're looking at the voltage over here, we know that the voltage is going to be 10 plus J0, right, in rectilinear complex number form. And in phasor form, it would be 10 volts. And of course, those are peak volts in case we're going to calculate power later on at an angle also of 0 degrees. But when we look at the impedance for the inductor here, we can see that the impedance is going to be, well, 0.1, and we already calculated what that was for the inductor last time, and that was omega L, right? So we know in general that what we've got is 0 plus J omega L. That's just a general equation, right? And then for Z sub C, I think everybody can see that we've really got 0 plus J minus 1 over omega C. So what we want to do is, since this is a minus here and that's a plus, if I was to add these two together and they were to come out to 0, what would that be? Right, so I want these to be added together so they come out to 0, because what are we going to do? We're going to find the equivalent impedance, right? So if we're going to find the equivalent impedance for that circuit and they're in series, then we want to add up the individual impedances, right? So the first impedance that we have is going to be 1 ohm plus J0, right? And of course, all these are going to be in ohm, so I'll just put that around there to begin. Oh, actually, I put the ohm in there, didn't I? Okay, well, whatever. And then plus the impedance of the, let's just put it down in its general form, and then plus the impedance of Um, and if you've noticed, what I've done is I've taken that negative out of the -1 over omega c, and I've just thrown it out in the front just so that we can add up these things, you know, together. And of course, those are all going to be ohms. And you can see that if we add these together, that there is a way that these two might cancel each other out. If omega L equals 1 over omega C, those two terms will cancel each other out, right? Because that would add up to 0. Omega L minus 1 over omega C has got to equal 0. So really what that means is, I mean, I can write it here, omega L minus 1 over omega C has to equal 0. And so you can see from algebra how we would get to this point right here. And of course, what can I do here? I can say, well, that would mean that omega squared equals 1 over LC, or omega equals 1 over the square root of LC. Does everyone see? I took the square root of 1 up there anyway, right? Because I have to do it in both the numerator and the denominator. But that gives me 1 over omega C. So there's a special frequency at which these two components, the inductor and the capacitors, reactances, are going to cancel each other out. And in fact, because they have 0 for resistance in both of their impedances are going to cancel each other out. Does everyone see how that works? So, and it's at a magic frequency, isn't it? Now we know that this is going to equal 2 pi f, right? Because I say omega, you say 2 pi f. So if we wanted to find out what that magic frequency was, we would just have that frequency is 1 over 2 pi times the square root of LC. And let's just do that calculation as soon as I get my calculator. I'm sorry. So let's do that calculation together. 1 over 2 pi times LC. So 2 times 3.14159 times 0.1 times 1 exponent minus 6 n parentheses taken to the square root equals 1 over equals 503. Is that what everybody got? I hope to God they did, because I sort of just picked these things out of my head as we go along. So 503.3 hertz. And I think I got something that was approximately, I mean, when I was sort of doing it in my head a little while ago, I got something that was approximately close to that. So there we go. And while we're at it, why don't we come up with what omega is? Because we'll have to use omega again, right? So omega being 2 pi f, that's just the frequency times 2 times 3.14159, and that gives us 3162. And what are my units? Radians per second. Because remember, what we're doing is we're zooming around the unit circle, aren't we? We're zooming around that unit circle. 3162 radians, you know, if you want to think of that in terms of degrees, that would be 181,198 degrees per second. And of course, if we wanted to think of it in total revolutions, it would be 503.3 total revolutions per second, or cycles, however you want to look at it. Okay, so that's what we were thinking about. Now I've got that point A, and I got this point B again. Remember what we were thinking about in terms of how this affects the voltage as we go around the circle. So let's say that we are at that frequency, that magic frequency, that resonant frequency. Resonant frequency. Right, so the resonant frequency is where the reactance of the capacitor and the reactance of the inductor cancel one another out. So we're at that 503.3 hertz, right? What's happening there? Well, we know what the voltage is, right? We know that the voltage is 10 volts peak at 0 degrees. And let's look at the voltage drop across that resistor. So the voltage drop over that resistor is going to be the current through the resistor times the impedance of the resistor. The current through the resistor, we can figure out from this, because let's add these up. If I add all of those up and these two cancel out, isn't the total the total impedance of the whole circuit, let's write it here, equals the impedance of just the resistor, doesn't it? Because the impedance of the inductor and the impedance of the capacitor have canceled each other out. So the only thing we have left is the impedance of the resistor. And so that's what we've got here. So if we wanted to find out what the current was, we just use Ohm's law. Let's, I always leave a place up here for Ohm's law, don't I? V equals IR. And we should put another thing up here too. P equals IV. Let's always remember that. P equals IV over there too. Two important equations. So I then equals V over R, right? Or in this case, I really should be using Z here. That would be V over Z, but you get the general idea. Because it's only resistance, I can say that it's 10 volts at an angle of 0 degrees divided by 1 ohm at an angle of 0 degrees. Right? So the current equals 10 amps. Now those, of course, are peak amps at an angle of 0 degrees. So if I put this here, 10 amps peak at 0 degrees times 1 ohm at 0 degrees, I get the voltage drop across the resistor. I'll put an R down there. Voltage drop across the resistor is going to be 10 volts at an angle of 0. Oh my goodness, well that's fantastic. It starts off at 10 volts at an angle of 0. And the voltage drop across the first resistor is 10 volts at an angle of 0. So that means that the voltage at A, right, is 10 plus J0 minus 10 plus J0 equals 0 volts. Fantastic. 0 volts, of course, plus J0. Because we're working in complex numbers, we always want to put that complex, that imaginary section in there too, don't we? That's the voltage at A. Now you're thinking, well, I know that the voltage here is also 0 volts, right? That's 0 plus 0 volts. But what's the voltage at B? Isn't the voltage at B just the voltage at A minus the voltage drop across the inductor? The voltage at A minus the voltage drop across that inductor. Let's do that. The voltage at B equals the voltage at A minus the voltage drop across the inductor. Right? So let's put those in there. Well, the voltage at A, we know what the voltage at A is. The voltage at A is 0 volts plus J0 volts, right? It's 0. And then minus the voltage drop across that resistor, or that inductor. The voltage drop across the inductor, that would be this, wouldn't it? Wouldn't that be the impedance of the inductor? let's look at the impedance. You know, we've written the impedance of the inductor out here in this form, but we haven't actually filled in those letters, have we? So let's do that. So the impedance of the inductor is 0 plus j omega L. 0 plus j. Now we know that L is 0.1 volts. And what is omega L? Well, 3162 radians per second, right here. That's omega, times L, which is 0.1, gives me 316.2. 316.2, right? And what is that? Those, of course, are ohms. So 0 plus 316.2. You know, I could write that in its phasor form as well, couldn't I? I could say that that's 316.2 ohms at an angle of, now look at it, you know, do I have to draw the complex plane again? I can. Here's the complex plane with the reals and the imaginary. And if I look at this, of course, this is all J, isn't it? Right? All J. So the angle I've got there is 90 degrees. So that's what my impedance is for the inductor that I've got right here. And that is the voltage drop we've got to take into consideration. Now, we know what the current is, right? Because this is just going to be the voltage drop, of course, here, right? That's just going to be the current times the impedance of the inductor. So the current, we already know in phasor form. The current in phasor form is 10 amps peak at 0 degrees. And we also know what the impedance of the inductor is. That's 316.2 ohms at 90 degrees. Does everyone see where I'm going with this? So V sub B, if we multiply these together, 10 amps times 316.2 ohms gives me 3,162 volts, right? Now, if this right here, let's just look at that all by itself. If that is 3,162 volts at an angle of 90 degrees. Does everyone see why it's 90 degrees? It's 0 degrees plus 90 degrees gives me 90 degrees. Then I could write this as, let's just look at this part right here. This part right here would be 0 plus J 3162 volts, right? Does everyone understand that? So let's add these two together. 0 volts plus 0 volts gives me 0 volts. And plus J 0 volts, and then minus, now remember there's a minus there, right? So it's minus this whole thing. So even though this is a plus here, there's a minus there. I know I'm saying this over and over because I forgot it on the last lecture, didn't I? Anyway, there's a minus there. So we've got minus J 3162 volts. So think about what B really is now, what the voltage at B really is. You're saying, oh yeah, it's 0 here, you know, it's 10 volts here, it's 0 volts here, and it's 0 volts here, but over here at B, it's 3,162 volts at an angle of 90 degrees. That's right. Yeah, you've just made some voltage there, haven't you? You've used the the properties of the inductor and the capacitor to create voltage, or I shouldn't say create voltage. We're just transferring voltage, right? So we've got 0 volts here, we've got 0 volts here, we've got 10 volts here, right at this point. I don't know, I'll call that Z. So we've got 10 volts there, but over here on this side, we have 3,162 volts. Now, you're probably saying, wow, that's fantastic. We can just make as high as voltage as we want. And yes, in theory, we can do that. And we do that because we take, you know, the voltage that we make at the dynamos and hydroelectric plants and everything like that. And then we ramp those voltages up super high. And we then send them out at super high voltages over those high tension power transmission lines in the electrical grid throughout the United States and the world. That's exactly what we do to get the voltage higher. This is sort of, but in your lab experiments, you'll never get up to 3,162 volts, by the way. But you should know that we can do that. You shouldn't, you know, think about a fluorescent light and the voltages involved in a fluorescent light, much higher. You know, how about a laser? We've got, you know, voltages in a laser that are very extremely high, very low current, of course, but very high voltages. Even in a TV set, that's why they say, you know, in the old TV sets, don't ever take the back off and work with it. You're going to kill yourself. And most people, I would say that probably pertains to. Now, so that's my voltage, and I call this the voltage maker circuit, right? And what do you want to do when you're making this voltage maker circuit? Well, you want to get the current as high as possible. And of course, I did that by reducing the resistance to as low a value as I can. And then you also want to get this over here. Now you can see that if I'm using a 0.1 Henry thing, that brings it up to this, right? Because I'm using it still at the 503 hertz or 3162 radians per second. But I could get this much higher, couldn't I, by just changing this to a 1 Henry thing and then running it at a different frequency that would make the 1 Henry and the 1 microfarad better, because you know, in the end, I'm always looking back to this. So you can see how you can change that and modify it. The truth is, there are no perfect inductors. You're always going to have resistance with any inductor because it's wound with regular magnetic winding wire. So that's going to be a problem, right? Okay. So I just wanted to point this out and show you what resonance is. And then also, you know, I guess we could look at the power in this circuit too. If we were looking at the power, you know, our voltage across any one of those things. Let's say that this one here, we're going to have a, you know, a voltage across there of 10 volts, and the current that's going through there is going to be 10 amps. So if I have 10 volts at an angle of 0 degrees times 10 amps peak at 0 degrees, divided by, of course, the square root of 2, because we have to change that from peak voltage or peak amperage into into RMS. And of course, and the reason I wait till the end to do this is I wanted to show you again what do we got here? We got the square root of 2 under 10 volts peak, and we've got the square root of 2 under 10 amps peak, right? So the square root of 2 times the square root of 2 equals 2. I love it when that happens. And so we find out that the power for this circuit is just going to be 10 times 10 divided by 2, which is 50 watts, right? So I've got 50 watts of power that is traveling from here to here, right? Now from here to here, I've really jumped up, haven't I, in the fact that I have this huge voltage jump between here and here across that inductor. Um, anyway, I think I might have gone on too long. I'm going to address those in the, in the, well, I don't know if I will or not actually, but the 316.2 volts across that inductor is the voltage, and the current through that inductor, but let's just do it. So that's for the resistor. And if we look at the power in the inductor, I've got 3,162 volts at 90 degrees across there, because this is 0 at 0 degrees. So the total is 3162 at 90 degrees. And then I'm going to multiply that by the current through there, which is 10 amps peak at 0 degrees. I'm trying not to go over that line. And so you can see that the power for the inductor is going to be, did I do that right? 31,620 at 90 degrees. And that wouldn't be, now these would be watts, but these would be volt amps reactive. I know what you're thinking, and in fact, we don't really use P sub L. We would use Q to talk about that, but that is the power through the inductor. The unfortunate thing is here that it really doesn't make any difference, because the power through the inductor gives it up one time and then lets it go. You know, I've shown you that before, that the current, the phases of the current and the voltage are different here, right? So they give it up and then they give it back, and then they take it and then they give it back, and they take it and they give it back. So there's no real power flow except for that 1/4 cycle of the wavelength. So this isn't stuff that's really lost, but this is stuff that's really lost. And I could do it also for the capacitor as well, because we got the same thing. And what you would find is that you would find for the capacitor, you would have 31,620 at -90, right? So in other words, the power that's being made here is being lost here, so forth, so on and so forth. Okay, well, that's going to be the end of this lecture, and I hope that I actually did this one right this time.